In this video, we're going to discuss how to find the equation of the inverse of a function. We've looked at how to take a table with a few points for a function and just switch the coordinates and get some points that would be on the graph of the inverse. But if we just have the equation of a function, we might want to be able to find the equation of its inverse. So that's what we're going to do here. So here's our steps. It's going to be helpful to use y instead of the function notation. So we'll start by doing that. And then we're going to switch where the x's and y's are in the function. So anywhere we see an x, we're going to replace it with a y. Anywhere we see a y, we're going to replace it with an x. At that point, we have the inverse relationship because we've switched x and y in the equation, just like to find the points for a table for the inverse, we took points from the original function and we switched the x and y coordinate of each one. So that switching of the x and the y position, that gives us the inverse. Then we just want to solve that for y because we want the equation, to say y equals something in terms of x. And then we can replace that y with the inverse function notation. Now, one thing we want to be mindful of is the fact that the function and its inverse should both be 1 to 1. And if that's not the case, we need to restrict the domain so that the function is 1 to 1. Essentially, here's what you're checking for. Because you've switched the x and the y column, if you think about the tables, right? If we have a table for f of x, and then we're going to want to make a table for the inverse. Whatever was in the x column, now we're switching, that's going to be in the y column, right? And then whatever was in the y column is now in the x column. So the domain for the function f is just the values that we can plug in for x, right? So that's essentially your x column if you could write out every single point in a table, which we usually can't because we have infinitely many points. But whatever the x values were for the function, that's the y values for the inverse and vice versa. So the domain of f is the range of the inverse and then the range of f, the outputs, are now the inputs for the inverse. So the range of f should be the domain for the inverse. So the domain and range switch is probably the shortest way to say that. The domain and range switch. So start by looking at the domain and range for the original function before you do anything. And then if you jot that down, that should help you remember at the end to check and make sure that the domain of the result you got is the same as the range of the original function. If it's not, then you might need to restrict the domain so that we have the correct inverse function. All right, here's our first example. We have this function x minus 2 cubed. You can probably picture that because it's your cube function shifted to the right 2 units. And the reason I'm drawing this is because that's, I think, the easiest way to think about the range of a function. Domain, you can look at the equation and say, well, if I plug in any real number for x, I get a real number output, no big deal. But for range, I think it's helpful to look at the graph. So the domain and range here are both all reals. We've looked at this function before. It goes forever up and down in both directions. So the range is all reals. It goes forever left and right in both directions. So the domain is all reals. So in this case, we're not really going to have to worry about restricting the domain for our inverse because even though the domain and range switch here, they're the same. and they're both all real numbers. So we're going to get a function that has the same domain and range as the original. So what we're starting with here is the function y equals x minus 2 cubed. And now we're going to find the inverse of that. So to find the inverse, I'm just going to jot down here, we know the inverse should have this domain and range. When we're done, we'll double check that. Okay, the inverse is going to come from switching x and y, just like we switched x and y coordinates in the table before. So everywhere we see a y, we're going to write an x. Everywhere we see an x, we're going to write a y. So this is the inverse of what we started with, but we'd like to write it so it says y equals. So to start solving this for y, we need to take care of what's on the outside first. So we need to take care of the cube by taking the cube root of each side. And then we can add 2, and we're doing that after the cube rooting, so that's outside of the radical symbol there. And so this is our inverse function. We can write it with the inverse function notation if we like. But cube root of x plus 2 is the inverse of the function that we started with. You'll notice it also has a domain and range of all reals because this is your cube root function shifted up 2. So it looks something like that. Alright, here's an example where the domain and range are not all real numbers. This is our square root function shifted to the left 5. So the domain is all reals greater than or equal to -5. You can't plug anything in for x that's less than -5 or you'll get a negative under the radical. And the range, the lowest y value we see is 0, and then we have all positive numbers as well. Alright, so starting with y equals square root of x plus 5, now let's talk about the inverse. The inverse then should have the domain of 0 to infinity, because that was the range of f. The y values are now going to become the x values, and the x values are going to become the y values. So that should be the range we end up with as well. So at the end, we're going to want to double check that we have the correct domain, and if we don't, we're going to want to restrict the domain to be what it should be. Okay, so to find the inverse, we switch x and y. So we're going to have x equals square root of y plus 5. That's the inverse. We want to solve it for y. To do that, we're going to need to square each side. And then we'll subtract 5. So we end up with y equals x squared minus 5. Now that might kind of stand out to you as a potential problem because we discussed in previous videos that quadratic functions are not one-to-one. A parabola does not pass the horizontal line test. This is x squared shifted down 5 here. This does not pass the horizontal line test, so this function's not one-to-one. Therefore, it can't have an inverse function, which means it can't be an inverse function because these should be inverses of each other, right? So what's the issue here? Well, we have the wrong domain, right? We have the correct range, -5 to infinity, but we have the incorrect domain here. This function allows for negative x values, but we didn't have any negative y values here. So if we're switching the columns, we shouldn't be getting any negative x values because we didn't start with any negative y's. So we're just going to restrict the domain here when we jot down what the inverse is. And we discussed this in a previous video too, that if you just delete the left half of the parabola, right, then it's 1 to 1, and then in this case we can see it would have the correct domain, 0 to infinity. So that's what we're going to do. We're just going to use the right half of the parabola. So when we say the inverse of f equals, we need to include that domain restriction, otherwise we're not giving an accurate statement here. So we would say this is the inverse function, x squared minus 5 only for x values greater than or equal to 0. This function is the inverse of what we had up here. Let's look at another example like that. Here we have negative square root of x minus 8. So this is going to be similar but a little bit different because we have that negative out front. This is, you've taken your square root function, shifted it to the right 8, but you also have a vertical reflection with that negative out front. So we take the square root of a number, we get something positive or 0, but then we're multiplying it by negative 1. So the domain here is everything greater than or equal to 8. And the range now is just 0 and all the negative numbers. So everything less than or equal to 0. Okay, so when we find the inverse then, domain and range are going to switch, so the domain of the inverse should be negative infinity to 0, because that was the range for the original. And the range is going to be 8 to infinity, because that was the domain of the original. Find the inverse. We're going to switch x and y. And you can multiply both sides by negative 1 if you like. It doesn't really matter which side the negative is on. We're going to square both sides, and a negative times a negative is going to give us a positive. So even if you multiplied both sides by negative 1 first and you had negative x on the left, when you square that, it's just going to be x squared because it's a negative x times a negative x. And then we're going to add 8 here, and once again we get a quadratic, so we need to restrict the domain because the entire parabola is not 1 to 1. This is x squared shifted up 8. Has the incorrect domain because this has domain of all reals. We want just the domain of negative numbers and 0. So now this time we want to include the left half of the parabola and the vertex because that would give us the correct domain. We want to be using negative x values and 0. If we use the right half like we did last time, that would be positive x values. So to determine which half of the parabola to use, you have to look at what your domain is supposed to be, and it's always supposed to be whatever the range was for your original. So in this one, the original function had positive y values, and so the inverse should have positive x values. So we used the right half there. Here, the original has negative y values, and so we want the inverse to have negative x values. So when we write down the equation for the inverse of f, we need to include that restriction, because if we just say, well, the inverse is x squared plus 8, that's not accurate. The inverse is x squared plus 8 for x values that are less than or equal to 0. because then we're just talking about this function, which is 1-to-1. All right, one more example here with a rational function. And we haven't dealt with rational functions too much yet, so don't worry too much about the domain restriction thing for these, because we can find the domain of this pretty easily by just saying, well, we don't want 2x plus 1 to be 0, so x can't be -1/2. But I'm just going to write here all reals except -1/2. But the range, again, you need the graph, and in this particular book we're using, we haven't talked about that yet. That's in a later chapter. So don't worry about the domain restriction for these, but I do want us to talk about how would we find the equation of the inverse. So we're starting with y equals 3 minus x over 2x plus 1. And the inverse then, now we have a couple x's here, so when we say switch x and y, we probably should be a little more, we probably should word that a little differently here. Everywhere you see a y, you're going to write an x. And everywhere you see an x, you're going to write a y. So that's going to happen twice. Okay, now we need to solve this for y, and we have y showing up in multiple places. So let's talk about how we're going to do that. First of all, we don't want y in the denominator. If you're solving for y, it shouldn't be in the denominator. So we're going to multiply both sides by 2y plus 1. Because then that will get it out of the denominator on the right side. On the left side, I'm going to go ahead and distribute in that x. So we were multiplying by 2y plus 1. So we're going to distribute that x into both terms. The second term was 1, so we're just going to have x for the second term. Okay, we're solving for y. When you're solving an equation, just think about like a really basic equation. You want to get all the terms with the variable on the same side, and you want to get all the terms without the variable on the other side. So the same is true here. We're focusing on y. That's our variable we're interested in. We want to get the y terms together. We want to get anything without y on the other side. So I'm going to add the y term to both sides here, and I'm going to subtract the term that doesn't have y. So on the left side, we had 2xy already. I'm adding y to both sides. X minus x is 0, and then over here we're adding those to get rid of the y, and then we'll have 3 minus x. So when you're doing this for a rational function, step 1, make sure there's no y's in the denominator. We took care of that. Step 2, get the y terms on one side, terms without y on the other side. We've done that. Now that you've done that, you can factor a y from both terms on the left because they both have a y. That's going to be y times 2x plus 1. And we do that because we only want to see one y floating around here, right? We just want y equals, and the other side shouldn't have any y's in it. So we're factoring out a y. Now we have y times something, and we can isolate y by dividing both sides by that expression. And now we have our inverse function solved for y. Now something interesting happened here. This inverse is the same as the original. So it is possible for a function to be its own inverse, and that's what we saw here. If you picture looking at the table for this function, if you take all the x and y's and switch them, you're going to get the same set of points. We have the point 0, 3 on this graph, for example. And we also have the point 3, 0 on this graph. So if we switch the coordinates for both of those points, we still have 0, 3 and 3, 0. So that is something that can happen. In this case, I know we didn't talk about this yet, but the range up here was actually the same as the domain. So like I said, when we get into graphing these, we'll talk about how to find their range. But their range was also all reals except -1/2. And so when you switch the domain and range, they're the same, and it's the same function, so same domain and range.